Welcome to the Explainer. If you've been tracking the massive explosion in artificial intelligence lately, you've probably realized it comes with a completely dizzying alphabet soup of hardware terms. I mean, we're talking DDR, GDDR, LPDR, HBM. It can be incredibly confusing to figure out what actually powers these giant AI models behind the scenes. So today, our goal is to decode that exact alphabet soup. We're going to trace the fascinating evolution of memory technology, look at exactly why AI has completely broken all the traditional memory rules, and explore the cutting-edge solutions that are making our AI future possible. All right, let's dive right into it. Here's our roadmap for today. We'll start by untangling the memory alphabet soup. Then look at how memory is tailored to specific needs. After that, we'll hit the big one, the AI Memory Bottleneck, followed by HBM, the 3D solution. Finally, we'll wrap up with the market titans controlling all this tech and take a quick look into the future of memory. All right, Chapter 1, the memory alphabet soup. Let's start with the baseline. Now, you already know that for most PCs and smartphones, the main memory is DRAM, super fast, but it forgets everything the second the power turns off. Historically, standard memory was called SDRAM, but then along came DDR, or double data rate. And honestly, the leap here was simple but absolutely brilliant. Instead of just sending data once per clock cycle, DDR sends data on both the rise and the fall of that clock signal. So if your clock is running at 100 megahertz, old school SDRAM gives you 100 transfers a second, but DDR, it instantly doubles that to 200. It effectively doubled memory efficiency overnight. And from there, it's just been this steady, chronological march of standard DDR memory heavily focused on boosting capacity and speed for everyday PCs and servers. Back around 2007, DDR3 was giving us maybe 17 gigabytes per second, jumped to 2014, and DDR4 bumped up to roughly 25 gigabytes. By 2021, DDR5 absolutely shattered previous records, pushing well past 50 gigabytes per second. It's just been a relentless, year-after-year pursuit of speed. Moving into Chapter 2, tailoring to specific needs. Because memory didn't stay one-size-fits-all for very long. This is where our alphabet soup branches out into two highly specialized paths. First up is LPDDR, with the LP standing for low power. This is all about ultra-low power consumption and tiny physical packaging meant to sit right next to the CPU. It's the absolute hero inside your iPhone, your Android, and Apple's M-series chips. Basically, it's what saves your battery life. On the other side, we have GDDR, or graphics DDR. This is custom built for GPUs, where thousands of computing cores are firing off at the exact same time. GDDR provides these massive, wide data pipes so you can instantly load up huge 4K textures and 3D data for high-end graphics cards, all the way up to the modern RTX 5090. But here is where the real drama starts. Chapter 3, the AI Memory Bottleneck. Because, look, standard computing and standard graphics, they are child's play compared to what AI requires. To really grasp the problem, you have to understand the completely different philosophies of a CPU versus a GPU. CPUs are highly focused on capacity. Think of CPU memory like this massive parking lot. It just needs to hold a vast amount of data so the processor can quickly grab things for sequential, one-at-a-time tasks. But GPUs, they are all about bandwidth. Because a GPU has tens of thousands of cores working at the exact same time, a parking lot doesn't cut it. It needs a massive multi-lane superhighway to move thousands of vehicles simultaneously. So here is the absolutely crucial point. The whole artificial intelligence boom relies almost entirely on those massive GPUs. But what happens when tens of thousands of hyper-fast AI cores scream out for data all at once? And standard memory, even really fast DDR or GDDR, just physically cannot send it fast enough. Well, what happens is total paralysis. We call this the memory bottleneck, and it is the ultimate hurdle for AI right now. The GPU asks for data, the memory basically says, hold on, I can't send it yet, and those incredibly expensive, ridiculously powerful GPU cores are forced to just sit there, idle, doing absolutely nothing while they wait. If you want faster AI, you can't just build a faster processor. You literally have to shatter this memory bottleneck. Which brings us to our hero. Chapter 4, HBM, the 3D solution. HBM stands for high bandwidth memory, and it represents a total paradigm-shifting leap in physical engineering. Instead of sitting far away on a motherboard, HBM is placed directly next to the GPU. But here's the crazy part. It's not just flat. It's 3D stacked like a microscopic skyscraper. To connect the floors of the skyscraper, engineers use something called TSV, or through silicon via. They literally drill microscopic holes vertically down through the silicon chips to connect them from top to bottom. Thanks to this 3D structure, HBM achieves a staggering 1024-bit bus width. To put that in perspective, standard DDR gives you a 64-lane road. HBM gives you a 1024-lane superhighway. And man, the numbers speak for themselves here. When we talk about sheer bandwidth dominance, standard DDR5 memory maxes out around 50 to 90 gigabytes per second. Specialized GDDR7 pushes that up to about 200 gigabytes per second. But a single stack of current generation HBM3E, it pushes over 1 terabyte per second. And since an AI GPU uses multiple HBM stacks, the total bandwidth reaches several terabytes per second. It is quite literally a completely different universe of speed. But as you might guess, this kind of performance comes at an astronomical price. HBM often makes up a huge chunk of the cost of an AI GPU. Why? Well, because the manufacturing ecosystem is insanely demanding. Drilling those tiny TSV holes, perfectly aligning 3D stacked chips, and maintaining the extreme high yields required, it's agonizingly difficult. On top of that, it relies on highly advanced packaging technology, like TSMC's CoWoS, just to bind the GPU and the memory together in the first place. It's not just a memory chip anymore, it's a full-blown structural marvel. So who actually controls all this tech? Let's get into Chapter 5, the memory market titans. When it comes to actually manufacturing these DRAM chips, just 3 companies control over 90% of the entire global market. You've got Samsung, the full-line global giant making basically everything, with immense strength in mobile LPDDR. Then there's Micron, the US leader, aggressively expanding its own HBM investments. But right now, the undisputed winner of the AI boom is South Korea's SK Hynix. They are the absolute global leaders in HBM technology, and they are driving incredible growth by completely dominating the supply of HBM straight to NVIDIA. Now, sure, there are a few other players out there, but looking at them actually highlights just how massive the technological gap is. Companies like China's rapidly growing CXMT or Taiwan's Nanya and Winbond, they're successfully producing standard DDR for industrial or automotive uses, but they're focused entirely on older tech or niche embedded stuff. Breaking into the extreme precision of advanced AI HBM remains incredibly difficult, and that exclusive club is still firmly controlled by those top 3 titans we just talked about. Which leads us to our final stop, Chapter 6, the future of memory, beyond the 2030s. Because the innovations on the horizon are frankly mind-blowing. Beyond just HBM4 and HBM5 pushing capacity limits even further, we're looking at things like CXL memory, a standard that will literally let multiple massive AI servers pool and share memory across the cloud. We're also seeing non-volatile alternatives like MRAM and ReRAM that sit right in the sweet spot between standard DRAM and your storage SSDs. And honestly, perhaps the most exciting of all, optical interconnects. We're talking about data centers literally beaming memory data over long distances using light instead of electrical wiring. No way, right? Which leaves us with this final, profound question to consider. As artificial intelligence models continue to scale exponentially, their appetite for data is basically approaching infinity. We've evolved from basic DDR to literal 3D skyscrapers of silicon just to keep up. But as we drill deeper and stack higher, will the absolute physical limits of human memory engineering eventually become the ultimate ceiling on how smart AI can actually get? Something to think about. Thanks for joining me on this explainer.